It's my pleasure to give a talk. Okay, and I just go ahead straight forward. My plan is to talk about some invariants of link from quandle rings. Okay, this is joint work with Mahinder and couple students, Brandon Nunez and Deepalis Way. I will quickly review quandles. Then I will talk about quandle rings and idempotents. Then I'll show invariants of links from quandle rings. And if there is time, I will talk about some algebraic properties of quandle rings and some open questions. I got interested in quandle rings a couple years ago when I saw a paper of Bardakov, Passy, and Singh on the archive. And I got interested in it. And then I started investigating quandle rings. One can think of them just parallel to group rings and quandle rings. I'm sorry. First, I recall the definition of quandle. A quandle is just set with the binary operation satisfying the following three axioms. And the first one comes from Reidemeister move 1, which is idempotency, x star x equal x. The second axiom, it says that right multiplication by every fixed element is a bijection. And that just comes from Reidemeister move 2. And the third axiom, which is right distributivity, it comes from the fact from Reidemeister move 3. If one draw the Reidemeister moves, you see these three axioms. Now, I just said that the second axiom says that right multiplication is bijection. We will denote its inverse mapping as y star bar x. Then we will use star bar whenever we have a negative crossing, and we will use star when we have positive crossing. Here are some examples of quandles. If you pick any set, you can consider what's called the trivial quandle, which is just x star y equal x for every x and y. Basically, it doesn't take care of y. You can think of right multiplication being identity maps. If you take a group, you can consider conjugation on the group, and this forms a quandle operation. Also, if you have a group, you can consider what's called the core group, which is x star y equal y x inverse y. Here it's easy to see that this is involutory quandle. If you do x star y, you go back to x. In other words, right multiplication is the inverse of itself. If you have any abelian group, you can consider what is called Takasaki quandle, x star y given by 2y minus x. In particular, if the group G is the integers mod n, we usually get what is called the dihedral quandle. I'm sorry?
Doesn't matter, continue.
Krishnendu, you can mute your.
I'm sorry?
Yeah, please continue.
Okay. If you take if you take a module over Lorentz polynomial, z of t inverse, you can consider the quandle operation given by x star y equal tx plus 1 minus ty. This is called the Alexander quandle because it relates to Alexander polynomial. Algebraists call this usually a fine quandle. You can think of x star y as like alpha x plus beta y. You will require alpha to be invertible. Okay. The reason for quandles is basically what's called the knot quandle. If you have a knot diagram, you can write a quandle presentation of it. And what's good about it is that we can, it was proved by David Joyce and Sergei Matveev that one can prove that two knots are, I'll talk about it in a moment. Let me first say what is the knot quandle, and I show an example. Take a diagram of the knot, color the arcs by elements of the quandle. And what you do is at each crossing, depending if it's positive crossing or negative crossing, if it's positive crossing, you use the relation x star y equals z. X is incoming, the color of the incoming arc. Y is the coloring of the over arc. It is positive crossing. X goes under Y, it produces Z. You get the relation X star Y equals Z. If it's negative crossing, you write X star bar Y equals Z. The quandle generated by the labeling of the arcs with this relation is called the fundamental quandle of the knot, or the knot quandle. Here is an explicit example. Consider the figure 8 knots. We have 4 arcs. We named them X1, X2, X3, X4. Then the fundamental quandle will be given by 4 generators, X1, X2, X3, X4. And you look at each crossing and you write the relation. If we look at the top one on the left, it is negative crossing. X1 is going under X3 to become X2. Then you get the relation X1 star bar X3 equal X2. And you do the same for all crossings. We have 2 negative crossings and 2 positive crossings. You write the relations, and then obviously one can simplify the presentation. Then here we can drop X2 and X4. Since X2 can be replaced by X1 star bar X3, and X4 can be replaced by X3 star bar X1, we get this presentation. You have only 2 generators and the relation. Obviously, we can make the presentation better if needed, but for right now, we will not worry about it. As I mentioned, or as I was talking about, the main theorem is this theorem of David Joyce and Sergei Matveev, which was proven independently back in 1980s. It says that 2 knots are equivalent if and only if their fundamental quandles are isomorphic as quandles. To be precise, equivalent mean either K is equivalent to L or L is the reverse mirror image of K. When you have a knot, you can consider its mirror image. If you have a knot, you can consider the reverse orientation. That's the reverse knot. And the theorem says that the knot K and L will have the same fundamental quandle or isomorphic fundamental quandle if and only if either K equal L or L is the reverse mirror of K. You see then the problem of classification of knots is turned into a problem of classification of quandle up to isomorphism. That's basically then the theorem is switching a topology problem to an algebra problem. Now, proving isomorphism of quandles is not an easy problem. It's also difficult. But what we do is we consider some representations, and then we are able to distinguish knots. Let me talk about some classes of quandles. A quandle is called medial if it satisfies the following property. If you have 4 elements, X star Y star Z star Y, you can swap basically the middle one, and that's why it's called medial. David Joyce called it abelian quandle, but abelian quandle may be misleading, thinking of it as commutative quandle. There is a reason why he called it abelian quandle, but okay, a quandle is Latin if left multiplications are invertible maps. In general, when you have a quandle, we do not require anything on the left multiplication. We only require right multiplication to be invertible maps. A quandle is semi-Latin if left multiplication are injective maps. In finite case, semi-Latin is the same as Latin, obviously. A quandle is faithful if the map sending X to inner X is the group generated by right multiplication, or S sub X. We call them the symmetry S sub X. And if this map is injective, notice that this is a quandle homomorphism. On the left, you have the quandle X. On the right, you have the group inner X, the group of right multiplications. You consider it with conjugation. Right distributive property is equivalent to taking this map and its quandle homomorphism from X to inner X with conjugation. Some examples of semi-Latin and Latin. If you take the core group of the infinite cyclic group Z, it is semi-Latin, but it's not Latin. It's straightforward to see this, mainly because 2 is not invertible in Z. More generally, if you have an abelian group, if you consider the core quandle mean X star Y equal to Y minus X. For the finite cyclic group, we call it the dihedral quandle. Then for any abelian group G, the quandle core of G is semi-Latin if and only if G has no 2 torsion. This is quick review of quandles. Now let me start talking about quandle rings. As I said, in parallel to group rings, Bardakov, Passy, and Singh introduced the notion of quandle rings, and take a ring K, a quandle X, and consider the formal combination sigma of over X in X of AX EX, exactly like you do in a group case. Obviously, these are we assume AX is 0 for all for almost all X, basically finite sums. And then you have a natural way of addition. You have an abelian group, and multiplication is defined similarly to the group case, except here, when we multiply the EX by EY, it is EX sub star Y, the quandle operation. Okay. In general, these rings are non-associative rings. That's what makes them a little bit difficult to manipulate or to deal with. Now, in groups, when you have a group and you take the group ring, you get an associative algebra or associative ring. Here, except for the trivial quandle, if the quandle is trivial, then the quandle ring is associative ring. If X is non-trivial quandle, the quandle ring is non-associative ring. And we'll see that quandle rings behave a lot different than group rings for many reasons. First of all, you can see that you cannot have left identity in a quandle. If you write E star X equal X, obviously X, you can replace it by X star X because of idempotency, and you can simplify X from the right. Thus you get X equal E. Then if there is left identity, the quandle is reduced to just that singleton. Then quandle rings in general do not have unity or unit element. Now here I'm talking about left identity. One can obviously look at the right identity. For example, if you take the trivial quandle, right identity means right multiplication by that element is identity. And for trivial quandle, you have any element have right multiplication being identity. We can talk about augmentation ideal, then consider the map epsilon from K of X, the quandle ring of X, to the ring K, by sending the combination sigma of AX EX to sigma of AX, similar to the group case. This is surjective ring homomorphism. You consider the kernel of it is two-sided ideal, and it's called the augmentation ideal. And then you have the ring isomorphism. K of X modulo the ideal is isomorphic to the ring K. You can write the basis element for the ideal. You just fix an element in X and you consider the EX minus E sub X naught. And if X has cardinality n, the ideal will have dimension n minus 1. Bardakov, Passy, and Singh, they characterize trivial quandle in terms of their augmentation ideal. They prove that the quandle X is trivial if and only if the square of the ideal is 0. Okay, now let me talk about invariant of links from quandle rings and idempotent. The number of coloring of knots by finite quandle, it's well known that it's not invariant. Basically, you consider quandle homomorphism from the fundamental quandle of the knot to your fixed quandle X, and you consider the cardinality. Now, this usually can be put on the computer. I use Maple to do this, and I consider I use knots in terms of braid because of the Alexander theorem, which says that every knot corresponds to the closure of braid. And from the website knot.info, you can get the braid notation for all knots up to at least 12 crossing knots. Okay, then what we're going to show is that using a quandle ring, we get stronger invariance. And this, we call it enhancements of the coloring invariance by quandle rings. We proved the following theorem, which says that if K is a link and X is a quandle, then if you consider the hom from the ring K of fundamental quandle of the knot K into K of X, the quandle ring of X, this is proper enhancement of the coloring invariant. I'll show a couple examples in a moment. Furthermore, if X is a medial, then this is proper enhancement. It is known that if you take hom of X, quandle X into quandle Y, if the target is medial, then hom become a quandle. This was done by Sam Nelson and Alisa Kranz. Now let me show an example, explicit examples. Consider the braid diagram of link K1. Now, this is taken from knot.info. You have the pictures here. The way we do coloring is just by putting a vector on the top and you push the coloring to the bottom, and then we close the braid to obtain the knot. Now for these two knots, K1 and K2, we can write the fundamental quandle as I mentioned earlier. Okay, you have for the knot K1, we have A, B, C, D, K. You have 5 generators, and you just write the relation at each crossing as we did earlier. Then this is the presentation of the fundamental quandle of the knot, the first knot, the fundamental quandle of the second knot, the one here on the right. This is a presentation. And then what we do is we focus on specific quandle, and then we consider, we hom the fundamental quandle into that quandle. It's easy. First, we consider the dihedral quandle with 6 elements. It's just integers mod 6. The quandle operation is just x star y equal 2y minus x mod 6. And we can compute the number of coloring explicitly, and they comes out to be exactly 12 for both of them. Then if you color these two knots by the dihedral quandle of order 6, you get 12 coloring for each of them, which means the coloring invariant does not distinguish them. But if we linearize and we consider hom we consider K to be the integers, and we consider Z of Q of K1, the target is Z of R6, we can prove that they are distinct. What we need is basically the idempotents over R6. We know R6 decomposes as every quandle has orbit decomposition. It's just the action of the inner group on the quandle, and R6 has 2 orbits, mainly 0 to 4 and 1, 3, 5. And each orbit is isomorphic to the dihedral quandle of order 3, Z3 with the star operation being x star y equal to y minus x. Then we can prove that we can distinguish them. The classical invariants, the coloring invariant did not, but when we use the quandle ring, we are able to distinguish them. Then this is stronger invariant. Let me talk about idempotents in quandle rings. sorry, how much time do I have? Hello?
Yeah, Prabhakar.
Yeah, please.
Can you hear me?
Yes, yes.
Okay.
You can continue for a few more minutes.
Okay, sure. I can stop whenever you want me to. I'm sorry.
Yeah, it's fine. As we
let's
started
consider
a bit late, you can continue for another 8 minutes.
Okay, perfect. Thank you. Okay. We consider the idempotents in the quandle ring. By definition, just the elements in the quandle ring such that U squared equal U, idempotent element. Here are a few facts. Since elements in quandle are idempotent, then the basis elements, we write them as E sub X, which is in one-to-one correspondence with elements of X. They are idempotent by definition because you have the idempotency in the quandle. Now, we are interested in the non-trivial idempotent. We say an idempotent is trivial if it's the form E sub X, and we're looking for non-trivial idempotent. If the cardinality of X is invertible in the ring, then one can see easily that's the 1 over cardinality of X, sum of E sub X for all elements of X is non-trivial idempotent of the quandle ring. Now, because of the augmentation map, since U squared equal U, obviously we get the augmentation of U is either 0 or 1. We will mention conjecture later. We also proved the following theorem. If K is a link and X is quandle such that the idempotent is a quandle, then we consider the set of idempotents. It's multiplication in the quandle ring. If it happened to be a quandle, then we get an invariant that is stronger than the coloring invariant. Then if you take cardinality of hom from Q of K, the fundamental quandle of K, into the idempotent of the quandle ring, which is a quandle now, this gives a proper enhancement of the coloring invariant. Same thing as in the previous theorem. If X is a medial, then you can consider the hom from Q, fundamental quandle of K into the idempotent, its proper enhancement. Let's consider the ring K to be just Z2, integers mod 2. And this gives this shows the power of idempotent in distinguishing links. Here is an explicit example. I'm avoiding all technicalities and no proofs. Consider the following quandle of 5 elements. Here I give it scaly table. We can compute the idempotent explicitly with Z2 coefficients. You have obviously the quandle itself, E1, E2, E3, E4, E5. And then we have 5 new non-trivial idempotent. Then this is a quandle of cardinality 10. And this contains the quandle, the original quandle, as sub-quandle. Now I consider these 2 links, the one in the braid form, obviously. The one on the left is just, if you close it, it's the half link. The one on the right, if you close it, that should be the torus knot T24. And then we can write the fundamental quandle of them. Now, the fundamental quandle of the half link is given by 2 generator AB such that A star B equal A and B star A equal B. That's easy to see from the diagram. The fundamental quandle of the other knot, it has 4 generators, as you can see from the picture, X, Y, Z, W, and you just write the equations at each crossings. Again, with the chosen quandle X being this 5 elements quandle, this one, with this quandle, we computed the coloring invariant. And this comes out to be that both knots have 13 coloring as the number of possible coloring by the quandle X. But if you compute the coloring by the idempotent, the first knot K1 has 68 colors, while the second knot has 76 colors. Thus, they are distinguished. Again, this is proper enhancement. Now I will talk a little bit about more algebraic stuff about quandle rings. as I mentioned earlier, except for trivial quandle, these are non-associative rings. One can consider, whenever you have non-associative algebraic structure, you can consider a weaker notion of associativity called power associative. You just pick one element. A ring is called, here ring mean in general. I don't mean, as Albert says, you consider ring meaning associative or non-associative. If every element generates an associative subring, it's called power associative. Basically, if you have just in associative ring, you can associate every random 3 elements as you like. In non-associative, you cannot do that. Then you'll focus on one element, X. And Albert gave this characterization of power associative rings. Bardakov, Passy, and Singh proved that the dihedral quandles are not power associative. Another property of the quandle rings, it's not, if the quandle is finite, it's not integral domain. You may have non-zero elements which multiply to give 0. And Bardakov, Passy, and Singh, they introduced the analogous of Kaplansky conjecture for quandles. Now, everyone knows, or in general, this is well-known conjecture of Kaplansky for groups. The Kaplansky zero divisor conjecture, which says that for torsion-free group and the field, the group ring has no zero divisors. The idempotent conjecture says for torsion-free group, the group ring has no non-trivial idempotent. Okay, in order to do the analogous of Kaplansky conjecture, they introduced what is called the unique products quandle. And this is the definition. It's parallel to unique products in groups. Then a unique products quandle, if you have for any 2 non-empty subsets A and B of X, there exists an element such that it has a unique presentation as products of A with B with A from A and B from B. Assume X is a domain, assume K is a domain, and X is an up quandle, then the quandle ring has no zero divisors. In order to state the analogous of Kaplansky zero divisor conjecture, they needed the following definition. A quandle is called inert if there exists finite subsets A from A1 to AN and 2 distinct elements XY such that if you multiply A by X from the right, is the same thing as multiply A by Y from the right. And they proved that for K integral domain and X non-inert and semi-Latin, the quandle ring has no zero divisors. If a quandle has trivial subquandle, then the quandle ring has non-trivial idempotent. The proof is one line. You just consider summation, and because the Y is trivial subquandle, when you compute U squared, you get the augmentation of U, then by B in 1, you get the result. We have the following conjecture. For all idempotents, the augmentation of the idempotent should be 1. Maybe I'll just move on and consider other cases. For conjugation quandle, if G is non-trivial group, then the quandle ring of the conjugation has non-trivial idempotent. This is a special case because you have the subquandle made by Xi, Xj form trivial subquandle. As an application to link quandle, we have the following. If L is link containing the Hopf link, and Q of L is the corresponding link quandle of L, then the quandle ring has non-trivial idempotent. From some computer experiments, we made the following conjecture. The integral quandle ring of semi-Latin quandle has only trivial idempotent. In particular, the integral quandle ring of finite Latin quandle has only trivial idempotent. And the proof should rely 100% on the right distributivity, as the following example shows. I give a magma that is all elements are idempotent. This is generated by from the computer calculation. This is Latin. Right multiplications are bijection, left multiplication are bijection, but it has an explicit idempotent. I write it here. U2 minus E3 minus E6 plus E7 is an idempotent in the quandle ring with Z coefficient. Again, the conjecture is with Z coefficient. If G, okay, this is the core quandle, just minus X plus 2Y. If G is an abelian group without 2 and 3 torsion, then the quandle ring of the core group has no non-trivial idempotents built with at most 3 distinct basis elements. Corollary, if n is coprime to 2 and 3, then if you consider the dihedral quandle R sub n, integers mod n, and you take the quandle ring over Z, it has no non-trivial idempotents built at most with 3 basis elements. We proved also some properties for idempotents. If X is a medial, if it's medial quandle, then the right multiplication by idempotents is ring endomorphism of the quandle ring. If X is finite, right multiplication by distinct idempotents gives distinct ring endomorphism. And I'll finish with this. Consider a longer knot up to isotopy. And then we have the following proposition. If L is non-trivial long knots, then the quandle ring of its fundamental quandle has non-trivial idempotents. And here are a couple references, and thank you.
Thank you, Professor Elhamdadi. Very interesting talk. Any questions?
Yes. As it is known that the quandle rings are Rec bialgebras. So could the algebraic properties which are important in your construction be interpreted in terms of the co-multiplication?
I believe, yes. Do you mean for the conjugation quandle?
For each quandle, the ring L, the quandle ring for each quandle is a Rec bialgebra. I suppose the idempotent properties, the general idempotents, could be characterized in terms of the co-multiplication. Do you know something about this?
No, I did not investigate that. It's an interesting question. I don't know the answer off the top of my head.
Thank you.
Thank you.
Any other questions?
Hello.
Yeah, any other
Sir, my simple question is that quandle ring, is it possible as a topological ring as study? Is it possible to?
You can, yes, that's something which can be done. You can start with a quandle that is topological quandle, and you can consider quandle ring of them. But obviously the tools will be lots. You have to bring some other tools or higher tools to deal with it. Yes. That's something which can be interesting, because topological quandle also give good invariant of knots. This was done by Rubinstein. He has a nice paper in which he defined the coloring invariance of with topological quandles. Yes, this is a good question. It's natural. Yes.
Is it there a particular reference about this? Particular reference about where the quandle ring is as considered the topological ring?
No. I don't think anybody has investigated this yet.
Okay.
To my knowledge, it's not. I don't know if Valeriy or Mahendra or someone, but to my knowledge, I don't think anybody investigated quandle ring of topological quandles.
My question is valid for a study of this type.
I'm sorry, I didn't understand the question.
My question is actually valid for the study of the topological quandle as a quandle ring. Is it possible? Is it possible that the quandle ring as suppose as a topological ring? That's my simple question. If you want to study.
Okay. You can consider the quandle X being topological quandle. Topological quandle means just the quandle multiplication is continuous.
Okay, okay, okay. Thanks.
That's one option. Obviously, when you bring the coefficient ring K, obviously you can consider topological ring. I mean, you can mix things and yeah. But to my knowledge, I don't think anybody has investigated this. But to me, it seems interesting question because just topological quandles give good invariant of knot. In fact, they relate even to Kuvanov homology from some paper of Rubinstein and forgot. Yeah.
Okay, okay. Thank you very much.
Thank you. Jacobson, I think there is paper on the archive. To my knowledge, it has never been published, but they compute the coloring invariant of knot by topological quandles, by spheres, by projective space, and they have some parallel to Kuvanov homology. And the
Thank you
reason
very
is because when you
Who's the author of that paper?
Rubinstein and Jacobson, if I'm not mistaken.
Yeah.
I think the paper has been on the archive and it has never been published. I think because of, I don't recall the details. I remember Charlie telling me some, yeah. But it's a nice paper. When you have topological quandle, the set of coloring has a topological structure. Then it's a lot richer than using finite quandles.
Okay. So any more questions? If there are no questions, let's thank the speaker.
Thank you all. And I'm sorry for the trouble to begin for my computer.
Mahendra, you want to say something?
Oh, Mohamed, can I ask you? Thank you for interesting talk. But I have one question. Suppose that we have free quandle of rank 2, 3, and so on, and we consider the quandle algebra over some good ring, for example, over integers. Do you know, is it true that the set of idempotents of these quandle algebras is trivial or not?
Yeah, Valeriy, we have answered this in our recent paper.
Yes.
I think Mohammed did not hear the question.
You know the answer. The answer is yes.
Yeah, we show that over integers, the quandle ring of free quandles of finite rank or countably infinite rank, they have only trivial idempotents.
Yes.
And the next question, is it possible to characterize quandles such that where quandle rings over integers, for example, have only trivial idempotents? Or you don't know this characterization?
We
Of
don't
course, you
know.
say that these quandles have these properties. What other quandles have these properties?
Valeriy, it's a nice question, but we don't know the answer. There are lots of things about idempotents in quandle rings, but we don't know.
Yes, there is a conjecture that Mohammed showed that for we believe that for Latin quandles, integral quandle rings of finite Latin quandles always have trivial idempotent. That's what Mohammed's computations showed.
Correct. And
So
I think I did.
Yeah.
I used some Maple computations, and it looked like it's the conjecture holds, but we don't know how to prove it. We couldn't even prove it even for if you take odd dihedral, take integers modulo an odd number. That's the Latin quandle. And even if you try to characterize prove it, it's not easy. You get a system of n equations, n unknown. It's Diophantine, but quadratic. It's complicated to solve. Now, some examples we can work them with computer, but we don't have a proof in general.
Yes, I understand that if you use the straight direction, you consider some system of equation. It's difficult to solve it, but maybe it's possible to find some other methods. What do you think?
Absolutely. Yeah. Direct try doesn't work. I mean, yes. Obviously, one can bring some other way of doing it, some other method.
Yeah.
Yes, that will be interesting.
There is
Yes.
yeah, Valeriy, there is some paper, I forget the authors, where they use some algebraic geometry techniques to say something about idempotents. Maybe, yeah.
Yes. It's interesting approach, I know. Thank you. Thank you.
Thanks, Valeriy.
Thank you. So any other questions? Okay, thank you. Let's thanks Professor Elhamdadi one more time.
Well, thank you all.